Hi class, how are you today? That's about two standard deviations away from what you said last time. The learning target for today is to be able to calculate and understand range, variation, and standard deviation. For a scale, 3, you can calculate and understand range, variation, and standard deviation. 2, you can calculate or understand range, variation, and standard deviation. 1, you can calculate or understand range. And 0, you cannot calculate or understand range. Let's get started. Section 3.2, Measures of Variation. The focus points for this lesson is find the range, variance, and standard deviation, compute the coefficient of variation from raw data, why is it important, and apply Chebyshev's theorem to raw data, and what does a Chebyshev interval tell us? Measures of variation. An average is an attempt to summarize a set of data using just one number. As some of our examples have shown, an average taken by itself may not always be very meaningful. We need a statistical cross-reference that measures the spread of the data. The range is one such measure of variation. The range is the difference between the largest and smallest values of a data distribution. For example, a large bakery regularly orders cartons of Maine blueberries. The average weight of the cartons is supposed to be 22 ounces. Random samples of cartons from 2 suppliers are weighed. The weights in ounces of the cartons were this. Compute the range of carton weights from each supplier. So the range is the largest value minus the smallest value. For the first supplier, it's 27 minus 17, which is 10. For the second supplier, the range is 27 minus 17, which again is 10. So the range of both of these is 10 ounces. Compute the mean weight of cartons from each supplier. In both cases, the mean is 22 ounces. Look at the two samples again. The samples have the same range and mean. How do they differ? The bakery uses 1 carton of blueberries in each blueberry muffin recipe. It is important that the cartons be of consistent weight so that the muffins turn out right. Supplier 1 provides more cartons that have weights closer to the mean. Or put another way, the weights of cartons from supplier 1 are more clustered around the mean. The bakery might find supplier 1 more satisfactory. Variance and standard deviation. We need a measure of the distribution or spread of the data around an expected value, either x-bar or mu. Remember that x-bar is for samples, mu is for population. Variance and standard deviation provide such measures. Formulas and rationale for these measures are described in the next procedure display. Then examples and guided exercises show how to compute and interpret those measures. As we will see later, the formulas for variance and standard deviation differ slightly, depending on whether we're using a sample, x-bar, or an entire population with mu. Alright, here's the procedure for computing the sample variance and sample standard deviation. There's many steps to this. So first, you're going to deal with having x. X is one data value in what you have, just one of the data values. To find the mean, x-bar, it's the summation of all the data values divided by how many data values you have, which is n. So n is the sample size, so you know how to find the mean. It's the average we're used to dealing with. Then you need to find the deviation of the mean, the difference. So in this case, we say x minus x bar. So x is one of the data values, and x bar is the mean. So you take a data value, subtract the mean, and do it for every data value. Then we have what's called the sum of squares. So what we're doing here is we're taking the difference of each data value, adding them all up and squaring them. Then adding them all up. So as it says here, the x minus x bar quantity is squared to make it non-negative. The sum is over all the data. If you don't square it, then the sum is equal to 0 because the negative values cancel out the positive values. This occurs even if some values are large, indicating a large deviation or risk. So you need to square them first, then add them all up. That's all we're doing here. After you find all the deviations, square all those deviations, then add them all up. So for sum of squares, this is an algebraic simplification of the sum of squares that is easier to compute. The defining formula for the sum of squares is the upper one, the one I just went over. The computation formula for the sum of squares is the lower one, but both formulas will give the same result. Whichever one you want to end up using is up to you. But really, you're doing the same thing in both. Sample variance. The sample variance is s squared. That's what we denote sample variance as. So like we said, sample mean is x bar, sample variance is s squared. The variance can be thought of as kind of an average of the sum of the squared values. However, for technical reasons, we divide the sum by the quantity n-1 rather than n. This gives us the best mathematical estimate for the sample variance. Again, the defining formula is on top, computation formula is on the bottom, but they give the same result. Then, finally, down to standard deviation, which is s. Variance was s squared. Standard deviation is s. So why do we take the square root? Well, if the original x units were, say, days or dollars, then s squared units would be days squared or dollars squared. We take the square root to return to the original units of the data measurements. The standard deviation can be thought of as a measure of variability or risk. Larger values of s imply greater variability in the data. Again, defining formula on top, computation formula on bottom, they give the same result. I always like going with the defining formula for all these. I find them easier, but to each their own. In statistics, the sample standard deviation and sample variance are used to describe the spread of data about the mean x bar. The next example shows how to find these quantities by using the defining formulas. As you will discover for hand calculations, the computation formulas for s squared and s are much easier to use. However, the defining formulas for s squared and s emphasize the fact that the variance and standard deviation are based on the differences between each data value and the mean. So, as I've shown before, here are the defining formulas, where x is a member of the data set, x bar is the mean, n is the number of data values, and the sum is taking over all the data values. Computation formulas. Again, the same with everything being the same. Here's an example. Big Blossom Greenhouse was commissioned to develop an extra-large rose for the Rose Bowl parade. A random sample of blossoms from hybrid A bushes yielded the following diameters in inches for mature peak blooms: 2, 3, 3, 8, 10, 10. Use the defining formula to find the sample variance and standard deviation. Several steps are involved in computing the variance and standard deviation. A table will be helpful, as I have here. Since n equals 6, we take the sum of the entries in the first column. Those are the numbers I gave you before. So the sum is adding them all up, which you can see down here is 36. And then divide by 6, because there were 6 numbers here, to get the mean. It says x, but that should be x bar. So we find the mean, which is 6, as you can notice is here. So we get the mean x bar is 36 over 6, which is 6. Using the value for x, we obtain column 2. So now in column 2, we take each data value and subtract the mean. So 2 minus 6 is negative 4, 3 minus 6 is negative 3, and so on to find all of them. Square each value in the second column to obtain column 3. Now we're taking all these and squaring them. Negative 4 squared is 16, negative 3 squared is 9, and so on. And then add the values in column 3, the sum of squares. So if we add all the squares up, we will get 70. So the sum of squares is 70. To get the sample variance, divide the sum by n minus 1. Since n is 6, n minus 1 is 5. So we do the formula. 70 divided by 5, the sum of squares divided by n minus 1, and we get 14. So the variance is 14. Now obtain the sample standard deviation by taking the square root of the variance. So we get the square root of 14, which is approximately equal to 3.74. In most applications of statistics, we work with a random sample of data rather than an entire population of all possible data values. However, if we have data for the entire population, we can compute the population mean mu. Population variance sigma squared and population standard deviation sigma. Lowercase Greek letter sigma, using the following formulas. So the little circle with a line coming out, kind of looks like an O with a hat or something. That is how we denote population standard deviation. So instead of S, we use lowercase sigma. Remember, uppercase sigma is how we say summation. So population mean is mu, which is the summation of all the data values x divided by n. N is the number of data values in the population. Population variance is sigma squared, so the sum of the squares divided by n, and the population standard deviation, the square root of the variance. Now we use n instead of n minus 1 because it is the population. We note that the formula for mu is the same as the formula for x bar, the sample mean, and that the formulas for sigma squared and sigma are the same for those as those for s squared and s, sample variance and sample standard deviation, except that the population size n is used instead of n minus 1. Also, mu is used instead of x bar in the formulas and sigma squared and sigma. In the formulas for S and sigma, we use n-1 to compute S and n to compute sigma. Why? The reason is that the capital N represents population size, whereas lowercase n represents the sample size. Since a random sample usually will not contain extreme data values, large or small, we divide by n-1 in the formula for S to make S a little larger than it would have been had we divided by n. Courses in advanced theoretical statistics show that this procedure will give us the best possible estimate for standard deviation sigma. In fact, S is called the unbiased estimate for sigma if we have the population of all data values. Then extreme data values are, of course, present, so we divide by n instead of n-1, because it's all of them. Comment. The computation formula for population standard deviation is. Now let's look at two immediate applications of the standard deviation. The first is the coefficient of variation, and the second is Chebyshev's theorem. Coefficient of variation. A disadvantage of the standard deviation as a comparative measure of variation is that it depends on the units of measurement. This means that it is difficult to use the standard deviation to compare measurements from different populations. For this reason, statisticians have defined the coefficient of variation, which expresses the standard deviation as a percentage of the sample or population mean. So instead of using units, we're dealing with percentages. If x bar and s represent the sample mean and sample standard deviation respectively, then the sample coefficient of variation, CV, is defined to be CV equals S over x bar times 100. And if mu or sigma represent it, then you use sigma and mu instead. Notice that the numerator and denominator in the definition of CV have the same units. So CV itself has no units of measurement, because if they have the same units, you're dividing the same units by the same units, and those cancel out to leave no units at all. This gives us the advantage of being able to directly compare the variability of two different populations using the coefficient of variation. In the next example, we will compute the CV of a population and of a sample and then compare the results. The Trading Post on Grand Mesa is a small, family-run store in a remote part of Colorado. The Grand Mesa region contains many good fishing lakes, so the Trading Post sells spinners, a type of fishing lure. The store has a very limited selection of spinners. In fact, the Trading Post has only 8 different types of spinners for sale. The prices, in dollars, are, and here they are. Since the Trading Post has only 8 different kinds of spinners for sale, we consider the 8 data values to be the population. Part A. Use a calculator with appropriate statistics keys to verify that the Trading Post data and mu being $2.14 and sigma being 22 cents. Solution. Since the computation formulas for x and mu are identical, most calculators provide the value of x only. Use the output key for mu, the computation formulas for sample standard deviation sigma, and the population standard deviation S are slightly different. Be sure that you use the T for sigma, sometimes designated as sigma sub n or sigma sub x. If you can find it easily, you can do that. If not, just ask me in class and I'll show you how to do it. Part B. Compute the CV of prices for the trading post and comment on the meaning of the result. So we take sigma divided by mu and multiply by 100. So we get 0.22, the sample standard deviation, divided by 2.14, the not sample, population standard deviation, population mean. That together will be 10.28%. Interpretation. The coefficient of variation can be thought of as a measure of the spread of the data relative to the average of the data. Since the trading post is very small, it carries a small selection of spinners that are all priced similarly. The CV tells us that the standard deviation of the spinner prices is only 10.28% of the mean. Chebyshev's theorem. However, the concept of a data spread about the mean can be expressed quite generally for all data distributions, skewed, symmetric, or other shapes, by using the remarkable theorem of Chebyshev. So what the theorem says is, for any set of data, either population or sample, and for any constant k greater than 1, the proportion of the data that must lie within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. So for the results of the Chebyshev's theorem, for any set of data, at least 75% of the data fall in the interval from mu minus 2 sigma to mu plus 2 sigma. So what that's saying is within 2 standard deviations from the mean. So if, say, the mean was 5 and standard deviation was 0.5, then the range there would be 2 times 0.5, which is 1, so 1 on either side of 5, so from 4 to 6. So in that case, 75% of the data would fall between 4 and 6. At least 88.9% of the data fall in the interval from 3 standard deviations on either side. So in the example I just used, instead it would be 1.5 on either side, so it would go from 3.5 to 6.5. And at least 93.8% of the data fall within 4 standard deviations. And for the example I used, that would go between 3 and 7. The results of Chebyshev's theorem can be derived by using the theorem and a little arithmetic. For instance, if we create an interval k equals 2, standard deviations on either side of the mean, Chebyshev's theorem tells us that 1 minus 1 over 2 squared, which is 1 minus a fourth, which is 3/4 or 75%, is the minimal percentage of the data in the mu minus 2 sigma to mu plus 2 sigma interval. Notice that Chebyshev's theorem refers to the minimum percentage of data that must fall within the specified number of standard deviations of the mean. If the distribution is mound-shaped, an even greater percentage of the data will fall into the specified intervals, and we'll talk about that in a future lesson. Here's an example. Students Who Care is a student volunteer program in which college students donate work time to various community projects such as planting trees. Professor Gill is the faculty sponsor for this student volunteer program. For several years, Dr. Gill has kept a careful record of X equals total number of work hours volunteered by a student in the program each semester. For a random sample of students in the program, the mean number of hours was X bar equals 29.1 hours each semester, with a standard deviation of S equals 1.7 hours each semester. Find an interval A to B for the number of hours volunteered into which at least 75% of the students in this program would fit. According to the results of Chebyshev's theorem, at least 75% of the data must fall within 2 standard deviations of the mean. Because the mean is 29.1 and the standard deviation is 1.7, the interval is x minus 2s to x plus 2s, which will be a range of 29.1 minus 2 times 1.7 to 29.1 plus 2 times 1.7, which, once you do the math out, is 25.7 to 32.5. So that's our interval. So based on that, we're saying at least 75% of the students would fit into the group that volunteered from 25.7 to 32.5 hours each semester. Now time for the sponge. A data set has the values 5, 7, 4, 11, 7, 10, 6, 8. And I want you to find the range, find the sample mean, find the sample variance, and find the sample standard deviation. Pretty much you're just following the formulas I gave you before. That's it for this lesson. Once again, please make sure to take notes on the entire lesson. Attempt the sponge. Put your rating on the scale from before, what you are at the top of your paper. Take a picture of everything or a video. Just make sure I can see it all and read it all. And have a good night.